back to Reinforcement Talking. Today we are honored to have Professor of Physics at UCL, who is also Royal Society University Research Fellow and an alumni of UCL Physics and Astronomy Department, Professor Ryan Nichol. Hello.
Hello.
Ryan's work mainly focuses on experimental neutrino physics. To elaborate, neutrinos are small particles, fermions, that interact via weak forces and gravity. They have small mass and are electrically neutral, hence the name neutrinos. One might question their importance. Neutrinos are produced in nuclear reactors and provide a source of heat for our planet in radioactive decay in the core. Joseph McLean and others wrote in their article, just as archaeologists study broken clay pieces to construct a story about the society that produced them, physicists examine neutrinos to learn more about the events and processes from which these subatomic particles have their origins. Experimental neutrino physics measures different properties of neutrinos that may help in understanding the evolution of the universe. AI could be applied to many fields within science, and today we will talk about how machine learning tools could serve for the better in particle physics. In what ways can AI methods be applied to particle physics?
Particle physics is one of those disciplines where it very much falls under the big data heading. So we have, and have had for years, these enormous particle accelerators that can produce, terabytes upon terabytes of data per millisecond. And for a long time, particle physics was right at the forefront of developing new machine learning techniques, such as some of the first neural networks, because they were just trying to work out ways of trying to keep up with this enormous flow of data. And I would say it's only in the last kind of maybe decade or so that things have switched around from particle physicists kind of teaching computer scientists about how machine learning works to the other way around. And we're really starting to gain great insights from the enormous developments that have gone on in machine learning, in computer science, in image processing, etc.
Yeah, I've heard in one of your articles you use multitask deep neural networks. Could you please explain what sort of neural networks they are and how could they be applied?
So probably our most successful recent use of deep neural networks is when on one of the experiments I work on, which is called NOVA, which is this long baseline neutrino experiment. So we fire these subatomic particles through the Earth from near Chicago to almost 1,000 kilometers away on the Canadian border. And what we get from our detector are effectively these complicated images of what happens when the particles inside were interacting. And what we're trying to do is we're maybe looking for the one neutrino event a day that will interact in our big detector near the Canadian border in comparison to the hundreds of millions of background events coming from things like cosmic ray particles and muons and electrons and various other things that are just background to us. So we have this enormous data reduction problem where we're trying to throw away all this background event and select these really kind of golden neutrino events. And so in 2016, we adopted this algorithm called the convolutional visual network, which was based on the kind of huge advances in image processing that people who were winning the ImageNet competitions in 2012 were using these deep neural networks like MobileNet and a few others. And so we basically took some architecture that had been shown to work in various image processing tasks and applied it to our neutrino data set to try and see if we could basically treat our data as though it was images and see if we could get the machine to sort the signal images from the background images.
What sort of properties of neutrinos do you use to kind of discern those neutrinos from the background?
So, as you mentioned earlier, neutrinos are these particles that only interact via the weak force, which means that neutrinos themselves are invisible in all particle detectors. So what you can detect instead is that if a neutrino comes into your detector, and to give you a sense of scale, our fire detector weighs something like 14,000 tons, and it's like kind of 20 meters high by 60 meters long, right? So it's an enormous, great big thing. And what can happen is that because these neutrinos only interact via the weak force, they can enter right into the heart of our detector and all of a sudden produce daughter particles in there, things that do have electric charge, like the electron or the proton. And so what we're seeing is the signals from these charged particles, but because of the topology where they get to suddenly be created in the middle of our detector, we know that it wasn't something coming in from outside, because it was only the neutrino that could kind of penetrate that far into our detector. And so in terms of the actual events themselves, we're just detecting charged particles that we could detect from other places, but because it's happening in the middle of this gigantic detector, we know that the only particle that could have got in that far is the neutrino. We also have, some of it we can do easily, knowing things like the time signature of when we were sending the neutrinos and the speed of light and these kind of factors.
Okay, so this is quite interesting, and I've also heard you are involved in the ANITA experiment in the Antarctica. Could you please tell a bit more about it and how you might use AI tools to detect the particles from space using these huge...
Yeah, certainly. So, I mean, ANITA is a very different experiment to NOVA. So NOVA is an experiment where we built our own beam of neutrinos and fired a sextillion of them through the Earth, and we caught, a few hundred. Whereas with ANITA, what we're doing is looking for the most energetic neutrinos in the universe that have come from active galactic nuclei or blazars or other kind of exotic astrophysics things. And so these are some of the most energetic particles in the universe. And the signal we're actually looking for is these neutrinos enter into the ice of Antarctica and produce a cascade of secondary particles. And those particles produce the sort of radio equivalent of a sonic boom. So because the particles are traveling faster than the speed of light in the ice, they can produce this really fast, coherent radio pulse. And it's those radio pulses we're detecting. And so in ANITA, we've had kind of 4 flights of the ANITA experiment that's kind of now finished. And what ANITA was is just a bunch of radio antennas dangling from a balloon in Antarctica, and spent maybe a couple of months in total flying around Antarctica. And what we're trying to do on that experiment is sort out these radio pulses that might come from neutrinos from all of the other sources of radio noise. And nowadays, that wherever humans are, there's loads of radio noise, but fortunately in Antarctica, there are very few humans still, but there are still lots of them. And so actually on the most recent couple of flights of ANITA, we flew a GPU processor on our payload in order to try to more efficiently sort out the signal from backgrounds. And although we weren't using fully machine learning techniques on that payload, the algorithms that we ran on our GPU, we did kind of train in using kind of lab generated signals and some kind of machine learning inspired ideas. But now there's going to be a big paradigm shift as we move from ANITA, which was effectively an analog instrument, to its successor, Pueo, which is a digital instrument, which means that we'll have to do this data processing maybe 10,000 times more quickly than we did before. And again, machine learning tools operating on kind of fast FPGAs are one of the ways that we're trying to approach doing this signal to background selection for that experiment.
So what sort of models are used in the new designed Powell, right?
Pueo. It's the name of a short-eared owl from Hawaii. That's
Could you please elaborate more? How is this speed up achieved, and whether the same models are used in the both of them, and whether the accuracy is comparable to ANITA?
It's very hard to. So I mean, one of the reasons that we have to do everything much quicker on Pueo is so it turns out the last ANITA flight was in 2016, so 6-7 years ago, but was using hardware that was maybe 5-6 years old at the time. And there's been enormous improvements in the processing power of FPGAs and various other bits of computing hardware, largely driven by machine learning needs in the kind of wider world. And so the sort of algorithms we're using, so what our Pueo data looks like is, you can think of it as just for each antenna, and we flying maybe 200 antenna channels on the instrument, you get a sort of voltage time waveform trace. And so many of the kind of relatively simple neural network approaches that people use to do things like monitor like heart arrhythmia, EKG type things, can be kind of directly adapted to what we're doing. Where going wholeheartedly down the machine learning approach with Pueo is difficult is that in the case of NOVA, we really understood what our backgrounds were, because they were coming from other particles interacting with our particle detector. Whereas in Pueo, what the signals that we don't want are various man-made signals, and we don't know what the people who we don't know where they are in Antarctica are doing to make these signals necessarily. And so it's much harder to model our background. So we try to go for a kind of more inclusive approach for Pueo, where we try to select any signal that could be potentially interesting, and then so that we save it and write it to disk on the balloon as it's flying around, and then after our flight we can recover it, and in our offline analysis we can then develop much more complicated machine learning inspired algorithms to do that analysis when it's not your only chance to do it. Because when you're making decisions live on the fly for which data you save and which data you throw away, obviously the stuff you throw away you can't ever get back. And so particularly in this case where we don't know like what new radio transmitters have been installed in Antarctica since the last time we were there, what new electrical furnaces have been operated, how many more snowmobiles there are in Antarctica than the last time we flew, that it's very hard to really have a completely kind of autonomous system operating from the start.
So I guess afterwards you could train, for example, again.
Yeah, so we using like a generative adversarial network to try to mimic these backgrounds is kind of one nice thing that we could try to do to see if we can really understand where they're coming from, and also using lots of the sort of dimensionality reduction problems to understand what the backgrounds are and where they're coming from. Fortunately, we are lucky in that there's no kind of the neutrinos we're looking for per year will maybe happen again. During our month-long flight, we might expect, a handful of neutrino events, whereas any of these man-made signals are going to be happening at much more frequent intervals than that. And so we hope by doing some kind of multi-dimensional clustering, and it's not clear, before we fly exactly what those dimensions are. Some of them you can imagine like location on the ice and various ways of characterizing the signal property. But others, there's lots of scope for thinking about it.
I see. Also, you mentioned that basically the neutrinos, when they approach the ice, they travel at the speed higher than the speed of light. How is that?
So it's more that when they inside the ice, light travels slower, right? So light if you look in, say, the radio regime, the refractive index of ice is about 1.7 or something like that. But if you make energetic charged particles like electrons and positrons, they'll be traveling at the speed of light in that medium. And so while you're in the medium, your energetic particles can travel faster than the speed of light, which is why you get this, it's called the Cherenkov effect, where you get this light equivalent, or in our case, radio wave equivalent of the sonic boom. And so you get this really very fast coherent pulse. And at the energies we're looking at, it turns out that one of the main forms of energy that's given out by the particle interacting in the ice is in the form of this very intense radio pulse, which is why we can fly a balloon above Antarctica and hope to see a neutrino interacting in the ice over 700 kilometers away. And then just the radio is going to kind of just hopefully get out of the ice and then travel through the air to our payload.
I see. Thank you for this clarification. So I guess within particle physics, there's a lot of different areas that could be potentially explored. Which one do you think are worth exploring in the future? In a sense that which directions apart from neutrino physics you think would be quite interesting to kind of approach to understand better using AI?
So, I think right now there's essentially no part of particle physics that will not, like the next decade or bit more than that, won't be entirely based on AI-driven algorithms. And for example, out in Switzerland, they have this particle accelerator called the Large Hadron Collider that generates lots of data. And in the next 10 years or so, they're going to upgrade it so it generates even more data. And when they do that, one of the most promising avenues that they've seen is the idea of moving to doing their event selection based largely off AI-driven techniques, where in order to process this data fast enough, they're going to be running all of those AI algorithms on custom hardware like FPGAs and GPUs. And so they're very much trying to keep up with this kind of fire hose of data coming towards them. They realize that the performance they're getting with the AI algorithms rather than the naive or conservative algorithms that they've been running with in the past are just much, much improved. And that transition is happening in essentially every other field of particle physics, where anywhere where you have large amounts of data, the AI efficiency is much better than the more conservative things that you can do in the past to make sure you don't make any mistakes. Now that you've got a big sample of data, you can start being more aggressive in your selection because you know what is and isn't there slightly better.
So with all the controversies going around about AI and AI being creative, do you think AI would be able to discover new physics at some point in the future?
I think that the role that AI is already playing in our current discoveries is really critical. So, for example, on NOVA, we mentioned earlier using this convolutional neural network algorithm. When we employed that for the first time in 2016 or thereabouts, it was the equivalent to almost increasing our data set by a factor of 30 or 50%. And so, that's just, running is the same as if you ran your experiment when this had been running for 10 years at the time for an extra 3 or 5 years. And so it's really making, kind of big step forwards. And as we go to these regimes where we've harnessing technological improvements along with machine learning, you're going to be able to probe whole kind of sectors of particle physics space that we just wouldn't be able to do any other way. And so you never know, what discoveries are in the future, of course, because otherwise you'd make them already. But the fact that we are able to harness these technologies and basically look in places we've never been able to look before means that we've got a much greater possibility of being able to make these particle physics discoveries in the near future than ever before.
Great. So I guess everything that's left is the scalability of the machines that perform the algorithms so that we can the more data we have, faster we can process it essentially. So like bigger GPUs.
Yeah. So scalability is a really interesting one. So if we go back to the Pueo experiment, Pueo is a really nice example of how technology is evolving. So I've been on ANITA and Pueo. I think the first flight I was involved with was something like 2004, 2006. So it's a long time now. And these are experiments where we're kind of dangling something about the size of a truck from a massive balloon in Antarctica, and we're getting all our power from solar panels. And so that meant that for the first ANITA, we could have maybe a couple of 100 watts of power to do all of our data acquisition, we call it. And there's been great improvements in solar panels. So maybe now that's doubled or so, but you're still looking at maybe using 500 watts or 800 watts of power in order to run this kind of process that is looking at kind of terabits of data per second. And so it's really a great challenge as to how can you process all of that data efficiently. And it's a nice kind of mirror for what you can do elsewhere. So when you're on the ground, it's very easy to be kind of blasé and just throw money at a problem and make a bigger farm and do everything else. But with something like Pueo, you're really limited by this resource of how much power can you get from your solar panels, and you can't use anything else. And that's really been our limiting factor. But the improvements in the last decade or so have really meant that we've gone from being able we've increased our kind of data throughput by something like 4 orders of magnitude. And it's really kind of starkly impressive how you can use evolving technologies efficiently to scale. And it's a nice kind of relatively kind of green story of where you can really make the most of these technologies rather than kind of the horror stories of heating up bits of desert, etc.
Okay, so we were happy to have Brian and Nichol with us today, and we'll see you next week. Tune in to listen more.